The world is moving toward clean energy. Cities want cleaner air. Industries want lower emissions. Countries want energy security. Hydrogen has emerged as one of the leading candidates to power this future. It can fuel trucks, ships, trains, industrial facilities, and even aircraft. When used in a fuel cell, it produces electricity with water as the primary byproduct. It sounds simple. Produce hydrogen, store it, move it, and use it. But hidden behind every hydrogen project is a challenge so difficult that it has driven decades of engineering innovation. The challenge is not making hydrogen. The challenge is storing it. At the center of the hydrogen economy sits a technology that most people never think about. A technology that determines whether hydrogen can move from the laboratory to the real world. This is the story of the most advanced fuel tank ever built. Hydrogen is unlike gasoline or diesel. Diesel can be stored in a simple steel tank at relatively low pressure. It is dense, stable, and easy to transport. Hydrogen behaves very differently. It is the lightest element in the universe. At normal pressure, it occupies enormous volume. To store useful amounts of hydrogen, engineers must compress it to pressures that would seem impossible in everyday life. Modern hydrogen mobility systems often store hydrogen at pressures reaching 700 bar. That is approximately 700 times atmospheric pressure. Imagine trying to contain a gas that constantly wants to escape while subjecting its container to forces powerful enough to destroy ordinary materials. Suddenly, the fuel tank becomes one of the most important engineering systems in the entire hydrogen value chain. When most people think of a fuel tank, they imagine a simple metal container. That approach works perfectly for gasoline and diesel, but it does not work for hydrogen. A conventional steel tank capable of safely containing hydrogen at 700 bar would be extraordinarily heavy. In some applications, the tank could weigh more than the fuel it carries. For transportation systems where weight directly affects efficiency, that is unacceptable. Engineers needed something stronger than steel, but significantly lighter. The answer came from technologies originally developed for aerospace applications. Instead of relying on thick metal walls, engineers created a completely new architecture built around advanced composites. At the heart of a modern Type 4 hydrogen tank is a polymer liner. This liner acts as the gas barrier and helps prevent hydrogen molecules from escaping. Around this liner, thousands of strands of carbon fiber are wound with extraordinary precision. Carbon fiber is remarkable because it combines exceptional strength with low weight. Pound for pound, it can outperform many traditional engineering materials. During manufacturing, robotic winding systems place carbon fiber at carefully calculated angles. Every layer contributes to the tank's ability to withstand pressure. Every fiber serves a purpose. What looks like a simple cylinder from the outside is actually a highly engineered structure composed of multiple layers working together as a single system. Inside the tank, the pressure never rests. Hydrogen molecules constantly push outward against the liner and composite shell. At 700 bar, the stored energy is immense. Engineers must account for pressure cycling, temperature changes, vibration, impacts, and decades of operation. The carbon fiber structure functions like armor. It carries the mechanical loads while the liner maintains containment. The relationship between these components must be perfectly balanced. Too little reinforcement and the tank becomes unsafe. Too much reinforcement and the tank becomes unnecessarily heavy and expensive. Every design decision represents a trade-off between safety, performance, durability, and cost. Safety is not an afterthought in hydrogen storage. It is the foundation of the entire system. Modern hydrogen tanks incorporate multiple layers of protection. Pressure sensors continuously monitor operating conditions. Temperature sensors ensure safe operation under varying environmental conditions. Leak detection systems help identify abnormal situations before they become problems. Pressure relief devices provide controlled release pathways if temperatures become excessive. Isolation systems allow specific sections to be disconnected if necessary. Every component is designed with redundancy and reliability in mind, because hydrogen leaves very little room for error. Public confidence in hydrogen depends heavily on the performance of these systems. Building one of these tanks is closer to aerospace manufacturing than traditional fuel tank production. The process begins with the liner. Once the liner is formed, it is mounted on specialized equipment where robotic filament winding machines begin their work. Carbon fiber strands are placed under carefully controlled tension, while advanced software manages winding patterns. After winding, the composite structure undergoes curing processes that lock the fibers into place. The tank then moves through machining, finishing, and assembly stages. Every step is documented. Every step is traceable. Precision is not optional, it is essential. Before a hydrogen tank can enter service, it must prove itself. Testing is extensive and often extreme. Engineers subject tanks to pressure levels beyond normal operating conditions. They perform burst tests, pressure cycle tests, impact tests, environmental tests, and fire resistance evaluations. Tanks may be exposed to vibration, humidity, temperature extremes, and mechanical stress. Engineers look for weaknesses, defects, and potential failure points. These tests are not performed because engineers expect failure. They are performed because safety must be demonstrated rather than assumed. Only tanks that successfully complete rigorous validation programs earn certification for real-world deployment. One question often surprises people when they learn about hydrogen storage technology. Why are these tanks so expensive? The answer becomes clear when you understand everything required to build them. Carbon fiber itself is costly. Manufacturing equipment is highly specialized. Quality control requirements are extensive. Testing programs are expensive and time-consuming. Certification processes involve significant engineering effort and regulatory compliance. Unlike commodity products produced in massive volumes, hydrogen tanks often require advanced manufacturing techniques and strict documentation standards. What the customer purchases is not merely a container. They are purchasing decades of engineering knowledge, advanced material science, and a system designed to safely contain one of the most challenging fuels ever used in transportation. When viewed individually, a hydrogen tank may seem like just another component. But when viewed from a systems perspective, it becomes something much larger. Hydrogen produced by electrolyzers must be stored. Hydrogen transported across regions must be stored. Hydrogen delivered to fueling stations must be stored. Hydrogen used in trucks, ships, trains, and aircraft must be stored. Everywhere hydrogen travels, storage follows, as the tank connects production to transportation. It connects infrastructure to mobility. It connects clean energy generation to real-world applications. Without advanced storage technology, the hydrogen economy simply cannot function. This is why the Type 4 hydrogen tank deserves far more attention than it receives. It is one of the hidden technologies enabling the transition toward cleaner energy systems. It represents the intersection of materials science, manufacturing, safety engineering, transportation, and infrastructure development. It is not glamorous, it is not usually featured in headlines, yet it quietly supports some of the most ambitious energy projects in the world. In many ways, it is the invisible backbone of hydrogen deployment. And this is only one part of a much larger story. Beyond the tank lies an entire ecosystem of technologies working together to produce, store, compress, transport, and utilize hydrogen. Electrolyzers convert water into hydrogen. Compression systems prepare hydrogen for storage and transportation. Storage facilities maintain energy reserves. Fuel cells convert hydrogen back into electricity. Refueling stations deliver hydrogen to vehicles. Ships move hydrogen across oceans. Mobility systems bring hydrogen into everyday applications. Together, these technologies form one of the most fascinating industrial ecosystems being built today. If you want to explore more hidden industrial systems like hydrogen storage, fuel cells, electrolyzers, compression systems, hydrogen infrastructure, shipping networks, and the technologies shaping the future of clean energy, visit H2 Hub by Renee Energy. H2 Hub is designed for developers, engineers, consultants, investors, and anyone who wants to understand how hydrogen systems actually work beyond the headlines. Explore the technologies, connect the systems, build a deeper understanding of the infrastructure powering the future. Because the future of hydrogen is not a single technology, it is an ecosystem, and every ecosystem begins with understanding the hidden systems that make it possible.